Ooh, nice. This is a nice one. So you have z equals x squared plus 1 sine y plus xy squared. Is that correct? By setting one variable constant, find a plane that intersects the parabola of z equals that in a parabola. What's the equation of a parabola? What do you need in there? Can there be a sign in there? Can you write the equation of a parabola with sign? Would it be a parabola if do you need to get rid of that sign is what I'm trying to get at. So what value potentially should you plug in for which? So first of all, what's a plane? What are the equations for planes? By setting one variable constant, so it's like x equals some constant or y equals some constant or z equals some constant, right? Exactly. So if we wanted to find a plane that intersects this in a parabola, which piece do we want to look at? Any ideas?
Like first distribute out the sine y.
You could distribute it out, sure. You absolutely could. Absolutely. So you could, if you wanted to, you could turn this into z, and it's in terms of x and y if you wanted to write it that way, is equal to x squared sine y plus what? Sine y plus xy squared. So if you wanted to just get rid of sine, what value do you have to plug in for which variable?
Plug in a constant for y.
Plug in a constant for y. Which constant? What's that going to be equal to? You're going to get, like, what are you going to get? You're going to get x squared some constant, right? Could we just, yeah, we could say, so let's just say it's equal to a. Sine of a plus what? Sine a plus what? A squared x. And what is this going to be? So we have x squared sine a plus a squared a plus sine a. What are all of those things involving a? No, not necessarily one. Not necessarily. We're saying they can be anything other than n pi. So the only thing we can say for certain is that all of these are what? Constants. Constants. So if we were to let y equal anything other, y equaling a constant, is that a plane? Y equaling a constant, is that a plane? It is a plane. Okay, so if we pick any constant other than n pi, we'll have a plane at some value that isn't n pi. You with me so far? If you want to find out where a plane, or if you want to find out where two equations intersect, what do? What's that most common method we use to find out where two things intersect? Set them equal to each other. Substitution, right? We set them equal, substitution. So let's say we let y equal some constant that isn't n pi. So something like pi over 2 or 3 pi over 2, something that isn't a multiple of pi. If we do that and we want to find the intersection between that plane and this equation, what do you plug in for y? You plug in that value. And what are we saying? When you plug in that value, what do you end up with? You end up with x squared times a constant plus a different constant times x. What shape is this right here? That is a parabola.
You're missing one.
What?
Like you're missing one variable.
So for this one, we're trying to find a plane. So this is a surface, right? This thing is like bubbling and doing weird things, right? We don't know. We're not looking at the general shape of it. We're trying to find a plane, like we did before, that when it intersects this surface, instead of getting a parabola, what are we going to get? Straight line. We're trying to find a straight line. So it's a plane that hits this in a straight line. If you take slices of a mountain, some of the slices might be a parabola, like we just found. But there are other slices that might be a perfectly straight line. A perfectly straight line. So, anybody have an idea? If we let y equal to pi, so z of x comma pi, you end up with x squared plus 1 times sine of pi plus pi squared x. But what is sine of pi? What is sine of pi? 0. So what happens to this first thing right here?
0.
It's 0. So you end up with z of y is equal to pi squared x. So that's a constant times x. That's a constant times x. Z is equal to a constant times x. Is that a straight line?
Yes.
Yay. If we want a sine curve, we better have sine in it. We better have sine in it. So what value, what are we going to substitute in for which value?
X in for 0.
Reverse that. Reverse what you just said. Not x in for 0.
I mean, y in for 0?
No.
0 for x.
0 for x. You had it right. 0 for x. Because if you plug in 0 for x, 0 y like this, what are you going to end up with? 1 sine y plus 0. Hey, look, there it is. Hey. Okay, so you scored on this one. So yes, you could check specific points. What else could you do?
Would you do cross section?
You could use cross sections. Absolutely. You definitely could use cross sections. Absolutely. You definitely could try using cross sections. Absolutely. What else could you try? You want to do B?
B, yeah, B.
I kind of want to do C.
Yeah.
I kind of want to do C first. Do the easier ones first.
Oh, okay.
So Ali, hi. Let's do C. Why do I like C, Stephen?
Just,
What's different about C, Stephen?
I don't know, but I like C.
Okay, you like C. Can someone tell me? Sure. You're like, it looks prettier. Can you give me a little bit? Ali.
No second variable, so you
There's no X, right? So it's independent of X. Meaning it doesn't matter what X is, the same height is going to be attained, the same Z value will be attained no matter what the X value is. So you go look over here. So which ones are independent of the X value? 1, 2, wait, which one? I think it's only 7. Look at 7. It doesn't matter what the X is, right? It stays, the values of Z stay the same. So hey, we just got one right there. So what is C going to be? 7. So we've done this one. Nice. Let's pick another one. What's the next one do you think I would pick? What? H.
Oh, wait, no.
I love H. So H is the absolute value of X times the absolute value of Y. So what does that tell you about the positivity or negativity of Z? It's always positive. And also, what kind of shape do you think it's going to look like?
It's gonna have like sharp ends because it flips it over.
It's going to have sharp ends?
Do you know what I mean?
Well, why is it?
Because you're never mind.
You can plug in negative X, you can plug in negative Y, right? But it's always going to be above the XY plane, right? Yeah, yeah.
Every axis that has to be 0. So or on the XY axis.
On the XY axis, so anytime X is 0 or Y is 0, it has to be a 0 height, correct? So anytime Y is 0, X is 0, it has to be a 0 height. Does anybody maybe see it? Where it is? Which one? 3?
Yes.
Yeah, it's kind of like stuck. It pulls it down. So hey, there it is. So we just got this one. So what is it? 3?
3.
Nice. Anybody want to guess what I'm going to try to do? Which one next do you think which one do you think I would pick next?
G.
G? Nah, I think D. Okay, you guys, you can figure. So I'm going to do D. So let's take a look at D. D is negative 1 over x squared plus y squared. So it's always going to be what? Negative. And as x and y get really small, the bottom gets really, really, really small, right? The bottom gets really small. So the overall thing gets really, really big, but it's negative, so it's going to go down. So as it gets closer to the z-axis, right? As x and y get small, you get closer to the z-axis. As you get closer to the z-axis, it's going to go down. So let's take a look at these. Is there one that spikes down? 1. There it is. So we have 1 right here. So number 1. Nice. So now it gets more fun. Excellent. Now it gets really fun. Which one do you want to investigate next? F?
It's kind of like D.
Nah. G? I like B. Let's go for B, shall we? You kind of like B? I kind of like B. So let's, at this point we could try to do the same methodology we just did, which was try to pick one where we can maybe figure something out about the shape itself given the equation. So in this case, as x and y get bigger here, you might want to think about symmetry. So x squared plus y squared. If x is 1 and y is 2, or if y is 2 and x is 1, you're going to end up with the same what value? The same z value. So if you interchange x and y, you're going to get the same z value. What kind of symmetry is that? Did we traditionally cut? It's like, is it? Nah, not if you switch x and y. No, what's it called? Symmetry around the origin. Symmetry around the origin. Okay. As x and y get bigger and bigger, what's the biggest value cosine can be?
1.
What's the lowest value cosine can be? 0, right? It's always going to be 0. Excuse me. Cosine could go to -1. Cosine can go between -1 and -1 and 1. But here's the thing about this. The input values here, what's the smallest you can make x squared plus y squared? 0. The smallest you can make it is 0. What's the biggest you can make it? It can get big. So the inputs are going from like 0 to whatever you want it, right? So is cosine going to oscillate a whole lot? From 0 to infinity,
Right.
how many times is cosine going to oscillate? Many times. So it's going to hit -1, -1, +1, -1, +1, -1, +1. So, but the thing is, it's going to keep on doing that. Let's look at these right here. Are some of these oscillating between higher and lower sizes? Like look at 2 right there. Is it getting really high and then does it get smaller and smaller and smaller? Do the ripples get smaller? So is it going to be 2? No, it's definitely not going to be 2.
It's all going to be the same.
Oh, what about 4 right there?
No.
No, that's not it. 5? No. Ooh, wait. What about 6 here? Could it be this one? It might be 6. It's not automatically wrong, right? So let's go back look at the other ones. Well, what about 8 right here? What's the minimum? What's the minimum?
0.
It's all positive, right? We know that at some point this is going to go to -1. So it definitely can't be 8. What about this one right here? What about this one? If this was the one we want, this point right here, what's that point right there? That's when x is 0 and when y is 0, correct? So if we do cosine of 0, what's cosine of 0? 1. So it looks like it goes down and then it goes up. So it's a circular symmetry. So right now we've narrowed it down to 2 of them. It's either going to be 7 or it's going to be what?
6 and 9.
Or 9. It's either going to be 6 or 9. 6 or 9. Those are the 2 numbers we're looking at. Now let's go back and look at 6 here for a second. Do you see some ridges on that one? Do you see some ridges? If this is correct, that's when x is 0 and when y is 0. What's cosine of 0? 1. So do you see that ridge right there? Do you see this ridge right here? What happens to the output value? So this right here is on the x-axis. So as I travel out this way, the x value is getting bigger or smaller? Bigger. Positive is towards you, okay? It's getting bigger. What's happening to the y value? It stays the same, right? So this is going to be like cosine of 0 and then cosine of something bigger and bigger and bigger. But here's the thing. If you keep on plugging in a different x value, it's going to be cosine of a bigger number plus 0 and then a bigger number plus 0. Is the output going to remain constant? Is the output going to remain constant? No. Do you see what I'm saying, everybody? On this what's the value of y as you travel along this ridge? What's the value of y? 0. The value of y as you travel along this ridge is 0. But what's happening to x? It's getting bigger. So then you're going to have the cosine of the square root of x squared, which is the cosine of x. What happens to the cosine of x as x gets bigger? Does it stay the same? No, what does it do? It's going to go up and down and up and down and up and down and up and down. But what does this ridge show you right here? It stays the same. So can it be 6? No. So which one does it have to be? 9. So now we know that this one is 9. So then you just have to keep up with a similar type of analysis. You eliminate them one by one, and it gets easier and easier. Then again, the equations, we pick the ones that we could deal with the easiest, so the equations get a little bit more complicated. But you have to do analysis like this. It's like factoring. There's no one good method for this. There's no one good method. I know that's not what you want to hear, but it's true. What's this, everybody? Have you ever seen something that looks like this? Yeah, kind of looks like the temperature map we had before, but let's look at the values. 1300, 1311,
Height.
Yeah, it looks more like height of some. So what kind of map is this? Anybody know what type of map this is? Topographical map, right. This is a topographical map. So it's interesting, even if you haven't really thought about how these are made, most of you should have an idea of like what they're actually showing. So if the lines are closer together, what's that mean?
It's hard. Like getting
Gets
it
higher.
right.
It's like a cliff. It's steeper, right. If the lines are farther apart, it means it's flatter. It's still, there's something changing, right? But it's changing less quickly. So the idea is you can look at a topographical map and figure out like, what's the steep path? What's the less steep path? For example, if I started on this point, and let's say I walked on this blue line, I would be staying at the same what? Height. The same altitude, the same height. Yeah, I'm using the same word. It's the same height from 0, whatever you want to call it, whatever your index is. But the idea is each of these lines represents the same height. The same height. In order also for a topographical map to be useful, it's usually, it has to be a consistent difference. What do I mean by that? What do I mean by that? For example, if this was 1,000 feet, and then this was 900 feet, what would you expect this one to be? 800 feet. Do you understand what I'm saying there? 1,000, 900, 800, then what? 700. What happens if they're not consistent distances? What happens if it's like 1,000, 999, 700? Does this map actually have any sort of meaning? Not really. I mean, you'd still have consistent heights, but it doesn't really tell you much by looking at it. So the difference, what heights each of these represents, has to be consistent, or it's really going to be hard for you to understand what's going on. So let's say this surface was in front on the ground right here. Let's say the surface was right here. So could we take some clay? Could we make this if we had a lot of time? Yeah, sure. Right, it depends. I mean, this is a pretty detailed surface here, right? My question to you is, if you have a surface, how do you turn it into a topographical map? How do you turn it into a how do you make a topographical map? So let's say we physically built it out of clay, okay?
Figure out how high it rises up to.
Okay, so you figure out how high, then
Each
what?
line represents like your independent model.
I understand what it represents, but how do you go about making the topographical map? Like literally, if you could do anything you wanted. What? Planes. Exactly. So if you have this topographical map, imagine it's rising and falling right in front of us. Can you see it, everybody? It's like rising and falling in front of us. Let's say I had a laser or a big sword. If I could just slice it parallel to the XY plane, so like z equals 10 feet, z equals 20 feet, z equals 30 feet, what am I going to get? I'm going to cut off like the top of a mountain, but that edge, what's that edge going to be? Oh, potentially this right here. Imagine I had a cone coming up in front of me, and I just sliced it at even intervals. What would I get? I'd get these circles, right?
Concentric circles.
Concentric circles, but each of the edges of those circles would represent these contour lines right here. Is this a cone? No. So you're going to get really weird shapes if you start cutting things?
Because mountains aren't cones.
Mountains generally aren't cones. Things in real life generally aren't perfect concentric circles. When you see perfect concentric circles, something's probably generating it. Okay, sit down. Lines, or level curves, that's another name for it, are obtained from a surface by slicing it with horizontal planes. A contour diagram is a collection of level curves labeled with function values. So, hey, have we looked at this before? Z equals x squared plus y squared? It's not. It's a we call it like a bowl. It's a parabolic bowl, right? It's a parabola that's spun around. You've actually seen it before in AB Calc. Remember you spun stuff in AB Calculus, all that. Slices. You're like, no.
Oh, so it's okay.
So what's going on here? We're making horizontal slices. Here's one where z is 2. Here's one where z is 6. What shape are we going to get every time we slice it? A circle. So you take those circles. Imagine if that circle is floating in space, floating in space, floating in space. And then what do you do with all those circles? They go down to the floor. So what do we get? This is what, if we look straight down, so this is the z-axis. I'm looking straight down. What do I see? I see a bunch of concentric circles. What's happening as you move further away from the origin? They're getting closer and closer together. So what does that mean about the bowl? It's getting steeper. What? It's getting steeper, not small. It's getting steeper and steeper, which makes sense because is it getting steeper and steeper? Yeah, parabola gets the tangent line gets, the slope of the tangent line gets larger and larger as you increase x and y in x squared plus y squared. So you can look at this a two-dimensional projection of a three-dimensional shape. A two-dimensional projection of a three-dimensional shape. There's cool symmetries here. There's lots of things. Now, can you come up with the exact equations for each of these? Yeah, there they are. We literally just plugged in z equals 2,
Because
z
of
equals 6.
horizontal planes, so that you
Exactly. Horizontal planes are z equals a constant. That's your big laser. That's your big sword. Kind of with me so far? They're fun. So, this is what I'd like you to do right now. See this one right here? Just the green one. See the green one right there? I would like you to draw me the contour diagram of what that looks like. Draw me a contour diagram. It does not need to be super, hyper, unbelievably accurate. I want to see what it looks like in general. The one in green, everybody. What does the general contour diagram look like? So it's the two-dimensional one. Don't draw this in 3 dimensions. Draw this in 2 dimensions. Recording. There we go. You end up with x equals 0 and y equals 0. So that means it's just the point 0, 0. What about z equals 1? You have 1 is equal to plus y squared. So what's another way to write that? 1 squared is equal to x squared plus y squared. What about z is equal to 2? So that's going to be the square root of. So what do we end up with? 2 squared is equal to x squared plus y squared. So let's just do one more. So 3 is the same thing, same process. We end up with 3 squared is equal to x squared plus y squared. What are these right here are the level curves. Those are the contours. Those are the level curves. Those are all what?
Circles.
Those are all circles. So if I were to draw these circles right now, what's the radius of the first circle? Well, the first one is just the point, right?
Oh, yeah.
So we have this point. And then z equals 1, let's say it's 1, 2, and 3. I'm just going to label those as 0, 1, 2, and 3. So the first one's going to be this dot right here. And then we have another circle. What's the z value for this one?
1.
So the height is 1 on that one. What about the next one? I'm doing my best on these circles, sorry. What do we got right there? Like this? And then what? 3. Let's see if I can do this arc. Wee! Whoa! And 3, and like this. What do you notice about the distance between each of the level curves? They're the same. They're the same. So it's a point, and then it's a circle, and then it's a circle. So what shape is this? Nope, it's not. It's the same. We just showed. We think it's the same. So what is it going to be? It's not it's a dot here, then it gets bigger and bigger. It's a cone. This is a cone, everybody. This is a cone. You see why this is a cone? It's a cone. The distance is, as you do this, what's the distance from here to here? It's the same as this, it's the same as this, right? Is it getting any steeper? No, it's staying the same. So basically, if you walked up, you'd be in the bottom of a cone, and no matter what direction you go in, it's always going to be the same steepness. Why? Because the distance from here to here is always the same. What happens if they get closer together? Well, it might bounce a little bit, or it might bend, but the idea is each of these, same slope in any direction, same slope. So this is a cone.
If it's a cylinder, then
Same. So if we do one more, I'll just do one last one here, sorry. What color should I use? Blue? If I use blue right there, we have here, here, and here, and there. So what's this one right here? That's the slope that's the contour line at z equals 2. I'm doing z's like the euro or something like that. So what happens with these lines? They keep on going this way, right? That's what the contour lines look like, right? Exactly. So it's kind of, this is a challenge because the contour line, it's not, these two, when you did the contours were all circles or all what? Lines. Is that going to be the case here? No, it's not going to be just one or the other. It is not going to be just one or the other. So let me give you a specific case. What happens when z is 0? What does that mean? 0 equals x squared minus y squared. So that means that y squared is equal to
X squared.
What does that look like? Be super careful. What do you have to do to both sides if you want to isolate y?
Square root.
So what does y equal? Plus or minus x. Careful. So you have two paths where the height is 0. And what are those paths? Well, they're right like this and like this. So this is where z is 0 and z is 0. But everywhere else, is it going to be a line? No, it's not. So let's change it a little bit. Let's say z is equal to, what do you want z to be equal to next? 2? Yeah, I like spacing it out a little bit. So if z is equal to 2, you have 2 is equal to x squared minus y squared. So what do you get? Y squared is equal to minus 2. So what does y equal? Plus or minus, what the heck does that look like? What is y equal to plus or minus the square?
Just plug in points now.
Does anybody know what that looks like? Well, what's the lowest point going to be at? When x is equal to what?
0.
So when x is equal to 0, it's going to be plus or minus.
No, you can't do that. X has to be greater than 0.
Square root of 2.
Did I make a mistake?
No. I mean,
X has to be at least square root of
Yeah.
0.
Oh, okay. So x can never be between the two, right? So this contour, what this tells us is a height of 2 is only reached
at square root 2 or negative square root 2.
exactly. So you know it's going to be at x is equal to, what is, let's say 2 or what? Oh, sorry, root 2 or what? Negative root 2. So what does this graph look like? Yeah, well, it looks like this, just to be careful. It looks like this on over here. This is the positive one. And what does the negative one look like? Looks like that. The positive one goes like this. The negative one goes like this. It has to, there has to be symmetry because when you plug in 4 or negative 4, you get the same one. So the upper half, just to be clear, everybody, the upper half is just when, so this is one graph, this is the other graph. They merge together. It's not, this is one function and this is the other. Is this a function? No, it doesn't pass the what? Vertical line test, exactly. So guess what all the contours really look like? All the contours are going to be similar to this, right? So that's a height though. What's the height here? Z is equal to 2. Z is equal to 2. That's where Z is equal to 2. So then you can start, yeah, so we plugged in 2 right there. The height is 2 right there. It's just the x value is root 2 and negative root 2. These are the x and y values right there. So could you draw concentric ones? Now, if you look at this, do you know what these are actually going to look like? Let me see if I can sketch this. It gets steeper and steeper. It kind of flattens out a little bit. It goes like this, and then it goes like this. They get closer together like that. What do you think it looks like over here? It's the same thing, but what direction does it go in? Sorry. It's the same shapes, but the heights here are going to get higher, right? It's going to z equal 2, then z is going to be higher. But what about over here? Z is going to go down. Do you remember this was that shape we looked at first, the hyperbolic paraboloid? It's got that bend in it, right? So going in these two directions, it's getting steeper. But going in these two directions, it's going down below the xy plane.
So it's like z equals negative 2.
Correct. But what will the contour lines look like?
The same.
Exactly like this, but they will represent different z values. The z values will go up when x goes up. Look, as x gets bigger, what happens? As x gets bigger, it pushes them out, they get bigger.
Oh, so if you put in like z equals negative 2, you know it's be bounded by square root of 2.
Correct. On the other direction, exactly.
Cool.
Exactly. So when you look at this, it's in your book. It looks like there's a lot of symmetries involved, but yet what you have to pay attention to is what z value each contour line represents. It's going up like this, and it's going down like that. It's kind of cool. It's kind of cool. In the middle, that's the xy plane. So do you see how the xy plane is represented right there? Do you see the blue right in the middle? There's a lot of blue in there, I'm sorry.
Why they can't use
Well, if that was common.
That's actually a really good question. But do you see what's going on here? The hyperbolic parabola looks like this. This is just the surface that you're projecting the contour lines onto. So when we were doing this, what happens as x gets bigger and x gets smaller? What happens? It gets higher, right? But what happens as y gets bigger and y gets smaller? What does it do? it goes down. But this curvature right here is exactly the mirror image of this curvature. So the contour lines, when you make your big sword slice, they cut the same path, but they represent different heights. They represent different heights. It's kind of cool.